Schrödinger and Heisenberg had quite a long battle over the right way of formulating quantum mechanics. But nothing compared to the epic struggle between Einstein and Bohr, two physicists who respected each other immensely, but who disagreed over what physics should aspire to be. For Einstein, there was always the hope that there could be a mind-independent reality that we could get as close to as our measuring devices and our calculational abilities would afford. For Bohr, there were fundamental limits to our understanding of the world. There were bounds incorporated into the uncertainty principle that Heisenberg had developed and that Bohr and Heisenberg had hammered out as an interpretive structure. But for Bohr, it was never going to be possible to aspire to the same kind of complete, deterministic, calculable world that Einstein had hoped to find. Let's go back to a series of conferences, the Solvay conferences, which we met already in an early stage where Einstein and Poincare had had their first and last encounter. But at the fifth Solvay meeting in 1927, some of these concerns that Einstein had raised met Bohr's objections in the beginning of the really intense part of the struggle between them. World War I was not only an intense struggle during the battle, it affected the educated classes enormously, and many of the scientists on all sides had been killed during the war. It left everybody with ferocious nationalist feelings and proclamations by scientists from France, Germany, and England, to the point where they were almost unwilling to be in the same room. At some risk, Einstein struggled to maintain relations between the belligerents. Even as late as 1927, there were difficulties. One handwritten note that I found in the Solvay archives noted that a participant would not be there because he said there'll be Germans present. Another memo to Lorentz on the 14th of October, 1927, I know that patriotism is intransigent as much in those who attack as those who defend. These are territories of an infinite sensitivity. But the Solvay Congress did convene in 1927, and present were some of the leading lights from all over the world, the people who were trying to forge a new understanding of this quantum domain. Erwin Schrödinger was there, Louis de Broglie was present, Werner Heisenberg was there, Max Planck, Lorentz, Einstein, Max Born, who went on to give the fundamental probabilistic interpretation of quantum mechanics, and Niels Bohr was there. You could see the people present as they began to argue. Walter Nernst, the physical chemist, Einstein, Planck, all of these people were struggling over how to understand what had just happened and was in the process of unfolding in physics. Even the seating at the table became an issue, where the king and the queen were present, and then in order of descending importance, the scientists were disported around them: Lorentz, Einstein, Bohr, Wilson, inventor of the cloud chamber, each of them taking their particular place in the hierarchy. Lorentz, the father figure of theoretical physics, the person who really presented a role model, even for people who otherwise disagreed hugely, like Poincare, Einstein, everybody always wanted to know what Lorentz would think. We want to make an image in our imagination, our esprit, he said. Until now, we have always wanted to form images through ordinary notions of time and space. These notions may be innate. In any case, they were developed by our personal experience, by our everyday observations. For me, these notions are clear, and I admit that I cannot form an idea of physics without these notions. The image that I want to form of phenomena must be absolutely distinct and defined, and we cannot form such an image except in space and in time. When Lorentz says they might be innate, what he means is, in the Neo-Kantian tradition, that it might be the case that space and time are built into us in a way that actually makes possible experience at all. In any case, Lorentz felt that all of his own successes, all of his detailed calculations that had made the electron fundamental to the new physics, explaining refraction and reflection, explaining the new phenomena observed on the new forms of spectra and what would happen to spectra if the sample was in a magnetic field, for example. All of that seemed to depend on having a picturable understanding of the microworld. Lorentz continued his reasoning by saying this: if we abandon old ideas, one can always maintain the old names. I want to conserve this ideal from older times of describing everything that happens in the world by distinct images. This was what Lorentz wanted. He pined after an understanding that was visualizable and graspable, and that we ought to keep that. We shouldn't abandon our ability to see things in this distinct way. But it was not to be. Lorentz died 3 months later, on the 4th of February, 1928. And Bohr and his younger colleagues were leading the world into a very different understanding of physics. Bohr said that we had, in a sense, to renounce those classical ambitions. He put it this way at the conference: the essence of the theory of quanta is that we must be content with considering representation in space-time and the principle of causality as complementary traits, though precisely the combination of these two characterizes classical theories. For Bohr, classical theories, and here he understands relativity, special and general, those theories, those classical theories, embodied both a space-time description of where objects were. Of course, space-time itself became much more complicated in the non-Euclidean world that Einstein had invoked, but you could have a space-time description of every bit of the universe, and you could give it a causal, deterministic understanding. These were not incompatible. They went together like hand in glove. One day, the philosopher from the Vienna Circle, Philipp Frank, also the mathematician, mathematical physicist, Philipp Frank had a conversation with Einstein. And Einstein was mocking quantum mechanics as saying that certain physical quantities could not be measured and so had been relegated to metaphysics and dismissed. Frank pointed out to Einstein that it was he, Einstein, who'd started that fashion. And Einstein replied, "Yes, but a good joke shouldn't be repeated too many times." Back and forth this argument went, and Einstein began, in his discussions with Bohr that became more and more intense, Einstein began to try to invent ideas or thought experiments that might be realized in a certain way that showed that he thought you really could speak about, say, position and momentum at the same time, that there was a reality to these things that reflected only our ignorance, not the impossibility of understanding. So here's an example of a thought experiment. He has a shutter that he can open and close really quickly, and so fix when the particle went through there, and in this way you could actually determine its momentum. You could close it completely and it would only go through one, or you could open and close it really quickly and determine from knowing the starting time to going through what its momentum would be. Well, Bohr said, that's not going to work, because if I have a wave packet and I only allow the shutter to be open a small amount, I make it go through as a packet. And we know packets are the same thing as all the different momenta, all the different wavelengths together. So as soon as I open and close really quickly, I force it into all sorts of momenta. But then, if it's got all sorts of momenta, I'll lose the nice interference pattern that I had before. I force it to act like a particle. If I have an experiment, Bohr said, that opens and closes the shutter really quickly, I make the thing go through as a packet and I lose any knowledge of what its momentum is. More than just knowledge, it is in many different momenta and I don't get the interference pattern. Okay, Einstein says. Well, suppose that I have a particle goes through, it starts out and it spreads out, it might go through both slits. Well, he says, let's take a device that's very carefully calibrated and I can tell how much momentum the electron imparts to the slit as it goes through, and therefore I can tell exactly whether it went through slit 1 or slit 2 and exactly what angle it's gone through at. Well, Bohr says, that's not really good enough, because if we imagine a device that would actually determine the momentum imparted to the slit, it might look like this. A slit that's mounted on very weak springs, so the tiniest momentum would be registered in a movement of this slit-containing window. Well, as soon as you do that, you have to figure out where the slit is in order to do this experiment. Well, by putting it at a particular place and locating it in space, we know from the uncertainty principle that I've made it a sum of all the different momenta. But if it has all different momenta, then the particle going through will get a kick of unknown amount of momentum as it goes through, and it'll change its wavelength, and so I won't get any interference on the other side. So it turns out the world is cleverer than Einstein in this respect, that if we try to measure its momentum as it goes through the slit, we're going to end up forcing it to be particle-like and not behave in the nice wave-like way that gives us this pattern at the photographic plate. So what Bohr says in sum is, Einstein, your attempts to do this are simply not going to work. All right, Einstein says. 3 years later, they meet again at Solvay 6 in 1930. Einstein's bowed but not defeated. Einstein says, quantum mechanics, according to you, forbids knowing simultaneously time and energy, just the way it forbids knowing momentum and position. In fact, they're very related. So Einstein says, what if we measure the time a photon is released and we weigh the source of light before and after the photon's released? Then we could get both the time and the energy, because we know that E equals mc squared. So we can just figure this out. We'll figure out if we suspend the device that's sending out the light by a spring and we measure it before and after it's released the photon, so we know how energetic that photon is, and then we have a clock attached to it, so we know when it was released, and we've defeated the uncertainty principle. And so what Einstein says is another case of ignoramus. We don't know, but it has a value of energy and the time of release, so if quantum mechanics doesn't represent that, it's incomplete. This is what Einstein keeps saying to Bohr, that there are ways to get around the uncertainty principle. So Bohr was really worried by this. He thought, oh my God, this is the end of quantum mechanics. We're really sunk. Einstein's got me now. But eventually he realized what was going wrong for Einstein. So suppose we weigh this clock machine. We have a spring and it's attached to a box with a source of light in it and a clock. So we weigh it. We look at where it is on the scale. We determine its position. Well, as soon as you determine the position of the box by the uncertainty principle, it must be in a combination of all different momenta. So it could be going up or down, and it could have a spread, including very, very big momenta. And the finer I measure its position, the bigger the spread of combination of momenta it has. And so in order to figure out how much energy it lost, and therefore the energy of the photon, we'll have to wait some unknown amount of time, greater and greater amounts of time as we determine the initial position more precisely. And it's a combination of different amounts of height as it oscillates back and forth from the kick it gets from that momentum that it's forced into by fixing its position. But here's the clincher. Bohr then says to Einstein, if it spends a superposition of all sorts of different heights corresponding to the different momenta, then it's at different heights, the clock is going to be running at different speeds by your, Einstein's, redshift blue shift. So there's an uncertainty in time because it's got an uncertainty in height, and the uncertainty in height makes the clock run at different rates because time depends on where you are in the gravitational field. So Einstein hasn't got Bohr sunk here, that Bohr says general relativity itself, the equivalence principle, guarantees that if we try to measure the weight of this thing before and after, we're going to have an uncertainty in height that's going to correspond to an uncertainty in the time that the photon is released. So it's not the case that there is a definite value of the time and the energy, and that quantum mechanics failed to get it. It's actually the case that there is an uncertainty here. And Einstein's own general theory of relativity is to be used to explain it. Einstein, says Bohr, you've been hoisted on your own relativistic petard. So what do we learn from this battle back and forth? We learned, first of all, that quantum mechanics for its originators was built on relativity, on the idea of critiquing the fundamental concepts of physics. And Bohr and Heisenberg pushed this farther by saying that it really threw into question the very idea of causality. They used the idea that we could measure things, and only when we could measure things could we assign them reality. And it turns out that measuring things did not include being able simultaneously to give position and momentum, or any of the other problems that Einstein tried to raise. And yet Einstein constantly was striving after completeness more than anything else, of representing every piece of physical reality in the theory. So far, as we've seen, he can't have it, but he did not give up. In 1935, he hit back, so 5 years later. But the fight against quantum incompleteness was a losing one, as we'll see in the next lesson. Einstein never gave up trying to make a subsequent theory to show quantum mechanics was incomplete. And Bohr never gave up, and his successors never gave up showing that quantum mechanics was as good as we were going to get with respect to completeness.